This is your presenter, Asloob Mudassar, and I am presenting slide number 18L of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: vibrational structure and Frank quantum principle, continuous spectra from molecular transitions. This is the 12th lecture of the series on molecular physics. I have already delivered 11 lectures earlier, starting from 18A to 18K. In order to understand this lecture, you should follow the previous continuous series of lectures from 18A to 18K. Vibrational structure and Frank-Condon principle. Vibrational structure is governed by the Frank-Condon factor, which has been described in equation number 217, which depends on the overlap of vibrational wave functions in the two electronic states. Remember that in the Frank-Condon experiment, we write an integral which constitute two vibrational functions. One vibrational function corresponds to the upper electronic state, whereas the second vibrational function corresponds to the lower electronic state. So the Frank-Condon principle actually depends on the overlap of vibrational wave functions in two electronic states. For that one, you can consult equation number 217. The absorption or emission occurs within a time interval short compared to the vibration period T vib of the molecule. So you see that a T vib, that is a T vibration, is actually the vibrational time period of the molecule. And the absorption or the emission transitions should occur in a time interval short compared with the vibrational time period of the molecule. The momentum P is equal to h nu over c of the absorbed or emitted photon is very small compared to the vibrating molecule. So you see that here we are comparing the two momenta. One is that of the emitted or absorbed photon with that of the nuclei. And here we are saying that the momentum of the absorbed or emitted photon is very small compared to that of the vibrating nuclei, and the momentum P of the nuclei is conserved during electronic transitions. The kinetic energy E kinetic is equal to P square over 2m stays fixed during the transitions. The average balance equation takes the form. So you see that this is h nu, which is, for example, emitted h nu. It is equal to the difference in energies between two vibrational levels belonging to two different electronic state. For example, E prime is actually upper electronic state, E double prime is the lower electronic state, E single prime is a vibrational level corresponding to the electronic state E prime. P double prime is actually a vibrational level corresponding to the lower electronic state E double prime. So each of these energy, that is E single prime as a function of V single prime, can be written as a potential energy plus the kinetic energy. And the potential energy corresponding to the upper electronic state is represented as E single prime potential of R plus E single prime kinetic of R. And minus times we are writing the E double prime as a function of V double prime is written in the square bracket, which is the potential energy in the lower electronic state, which is E double prime pot as a function of R, plus the kinetic energy corresponding to the electronic state in the corresponding to the lower electronic state is E double prime kinetic as a function of R. Now you see that here in the third step I am writing E prime of a potential as a function of R star. You see that here I am writing R star minus E double prime potential as a function of R star. Because R star is the distance between the two nucleus, between the two electronic states in a molecule at which the kinetic energies become equal to each other. So when the kinetic energy becomes equal to each other, the kinetic energy part will be cancelled out from this equation, that is from equation number 226. and the energy of the photon which is emitted during the process will depends upon E prime of a potential as a function of R star minus E double prime potential as a function of R star. That is, the electronic transition takes place at a nuclear distance R star, where the kinetic energy in the upper and the lower states are equal. So, when the transition occurs with a nuclear separation R stars, then the kinetic energy of the molecule in the upper electronic state and in the lower electronic state will be equal to each other, as shown in equation number 227. That is, E single prime kinetic as a function of R star is equal to E kinetic double E double prime kinetic as a function of R star. So these two kinetic energies belonging to the upper electronic state and the lower electronic state at a specific distance of the nuclear separation R star will be equal to each other. The difference potential U of R introduced by the Mulliken and as given below is plotted, has been plotted on the next page. So first of all, let me show you this Mulliken potential, which is the difference of a potential between the between the potential energy in the lower electronic state minus the potential energy in the upper electronic state plus the potential energy of the total energy of the molecule when it is in the vibrational level V single prime of the upper electronic state. So due to that one, you will get U of R, which is the difference potential, and it is called the Mulliken potential and has been defined as given in equation number 228. So first of all, let me explain this potential using the diagram which has been referred. See the figure on the second next page. That is this one. So you see that in order to explain it very quickly, I am showing you the lower potential curve, the lower electronic state with the potential E double prime potential as a function of R. And then E single prime potential as a function of R is the potential corresponding to the second electronic state. I am considering two vibrational levels. V double prime is the vibration level in the lower electronic state, and V single prime is the vibrational level in the upper electronic state, shown by the horizontal lines. And you see that I have shown two transitions. One is at R1 star, that is from the vibrational level V double prime to the vibrational level V single prime, and similarly at R2 star, occurring again between the same levels but at a different value of nuclear separation R2 star between the two vibration levels V double prime and V single prime. And these transitions have been indicated by these double-ended arrows. One at R1 star, that is when the nuclear separation between the two nuclei is R1 star, and when the separation between the two nuclei is R2 star. The two transitions have been shown between the two same vibrational levels belonging to lower electronic state and the upper electronic state. Now let's talk about the U of R, which is the different potential. Now you see that in the definition, what I do is that I subtract E1 potential from the E double prime potential. That is, the upper potential is subtracted from the lower potential. You know that the upper potential has a higher value in comparison with the lower potential. So when you subtract upper potential represented by E single prime pot from the lower potential represented by E double prime of a potential, you will get a negative, you will get the difference which is negative, which is a negative quantity. So in order to make that quantity a positive quantity, I have added the energy belonging to E single prime, that is E as a function of V single prime. So this energy was added to that difference of a potential in order to make U of L to become a positive quantity, so that we can plot this as a red curve on this plot. Otherwise, this red curve will be below the zero axis level. And you know that I have, let me talk about the definition U of R, that is the molecular difference potential is equal to the lower potential minus the upper potential plus the energy of the molecule when it is the vibration level E1 of the upper potential. So this adding E of V prime will make the U of R to appear as a positive quantity, and that is why UR has been plotted as a positive quantity with the dot with the dashed red line or a red curve in this diagram. So U of R difference potential has been shown as a dashed red curve on this plot. And simply you see that, let me remind you again that it is the difference of potential of the two levels, that is subtracting the potential from the upper level, that is subtracting the upper level potential from the lower level potential, and then adding this quantity U of H prime to make U of R to behave like a positive quantity, so that we can plot U of R, that is the different potential, as a dashed red curve on this plot. And this is the definition given by the Mulliken difference potential. So the difference potential U of R introduced by the Mulliken and as given and as has been explained in the diagram is given mathematically by U of R is equal to potential and potential corresponding to lower electronic state minus potential corresponding to upper electronic state plus the energy of the vibrational level from the upper electronic state from which the transition is going to occur. The electron jumps from one electronic state into the other, which takes place at such a value of R star, where U of R star intersects the horizontal line E of V double prime at two points, R1 star and R2 star, which I have explained in the diagram. So you see that here this difference of potential interacts with the horizontal vibrational level, which is V double prime level, and the energy corresponding to this one is E of the V double prime. So the red line, so the red curve, that is the Mulliken difference potential, interacts with this vibrational level at 2 points corresponding to R1 star and R2 star. So you see that we can write U of R star is equal to E of V double prime, because U of R star interacts this vibrational level V double prime lying in the lower electronic state at two points, R1 star and R2 star. So we have generally written this expression for the Mulliken difference potential, that is U of R star is equal to E of V double prime. Now you see that this curve, which you know that I have explained this curve, which is next to this one. This curve has been explained. This curve, that is the upper one, will be referenced in the paragraph that we shall follow after some time. So let me explain this one so that I can, when go through the next paragraphs, you can understand what I am talking about after having studied this diagram. So first of all, the caption, illustration of the Frank-Condon principle for vertical transitions, that is between the vibrational levels with the delta V is equal to 0 in part number A. You can see that in part number A, the transition occurs for a delta V is equal to 0, that is between the same vibrational levels from the upper electronic state and from the lower electronic states. That is where delta V is equal to 0 for part A. And for part B, you can see that the transition occurs between two different vibrational levels from the upper electronic state and from the lower electronic state. That is delta V is greater than 0. because the upper vibrational quantum number V single prime is greater than the lower vibrational quantum number V double prime. So the difference delta V, which is equal to V single prime minus V double prime, delta V is greater than 0 for this transition. And you know that for this transition, you will notice that I have shown a dotted projection on the horizontal line, which belongs to Re single prime, because this is the projection of the minimum point, that is the equilibrium separation on the horizontal axis. So this represents the separation from the separation equal to Re between the two nuclei. So this Re single prime is actually the equilibrium separation between the two nuclei when they belong to this electronic state. And this lower electronic state has an equilibrium separation Re double prime. Now I am considering the transition from the value where the nuclear separation was Re double prime to the upper electronic state, which has an equilibrium separation equal to Re single prime. And the transition is shown between different vibrational levels, V single prime and V double prime, which is the lower level. So these are two different levels. And for this one, the transition follows delta V is greater than 0. So these are delta V. This is delta V is equal to 0. This is delta V is greater than 0. So let me now go through the caption of this figure. Illustration of the Frank-Condon principle for vertical transitions with the delta V is equal to 0 in part number A and the delta V greater than 0 in part number B in case of potential curves. For the first case, the potential, the separation Re double prime was equal to Re single prime, and for the second case shown in part number B, the Re single prime is greater than Re double prime. And you know that for this one, for the part number A, I have plotted the Frank-Condon principle, that the probability transition has been plotted for this horizontal vibrational level, and for this upper vibrational level, the Frank-Condon principle, that is the transition probability, has been plotted. You know that when there is a large peak, there is a high transition probability. But when the peak is smaller, for example, in this region, the transition probability will be smaller. Similarly, the transition probability has been discussed for the upper electronic state in part number B, and also the transition probability has been discussed for the initial vibrational level of the lower electronic state following the Frank-Condon principle. Now you see that I have explained this diagram. Now let's go through the text. The probability for a transition from the vibrational quantum numbers V single prime to V double prime and vice versa is given by the Frank-Condon factor. So you see that it is the Frank-Condon factor that determines the probability of transition, and it is just I explained using the previous diagram. The probability that a transition takes place in the interval dr around capital R is given for, by which has a maximum at R is equal to R star. So you see that the Frank-Condon probability is maximum when we consider the transition from R in the region of dr and R is equal to R star. When R is equal to R star, the Frank-Condon probability, transition probability will be maximum, and that is given by this integral. It is a P of R, that is the probability that the transition will occur at a distance R multiplied by dr. So this left hand side means that we are going to determine the probability, Frank-Condon probability for the transition at a distance R, in a region dr centered around the value R. And this is given by the integral, that is the wave function y single star b y star y single star as a function of r minus y double star as a single of r. So you see that y single star vibrational is actually the vibrational wave function belonging to the upper electronic state, and the y vibrational double star is actually the wave function corresponding to the lower vibrational wave function. And you see that I have multiplied dr, and I have taken the integral of the numerator in the denominator, so that the probability should always be less than equal to 1. So you see that if you want to determine the probability which is given by the Frank-Condon principle, probability of transition is determined by the equation number 230 using the wave function of the upper vibrational level and the wave function of the lower vibration level. If E single prime, if a potential corresponding to E single prime and the potential corresponding to E double prime have similar R dependence at Re single prime is equal to Re double prime, that is at the equilibrium separations, these two potentials have the same dependence on R. The Frank-Condon factor for the transition with the delta V is equal to 0 is maximum. Which I have shown in part number A of figure number 150 on page number 150. So you can see that with the same, that is for example, from Re, for example, for the lower state, where Re double prime is equal to Re single prime, look at this transition. This transition will have the maximum probability when Re double prime is equal to Re single prime. Similarly, the same probability transition will also be observed at different locations, because both V single prime and V double prime are the same levels, and the transitions have been is being considered at different locations from the center of this nuclear separation. The reason is that this transition and the transition in the center, they have the same values. It is because the potential corresponding to E single prime and the potential corresponding to E double prime have the same dependence on capital R. That is, the curves are identical. That is, the black curve and the red curves are identical. And you see that when you have the same dependence, that is when these two potentials have the same dependence, then of course at delta nu is equal to 0, you have the maximum Frank-Condon factor. But when there is a deviation between the two potentials, then of course, or otherwise, if you consider delta nu not equal to 0, then of course the Frank-Condon principle factor will give you a smaller value. The larger the shift delta R, which is equal to Re single prime minus Re double prime. If the shift is larger, that is delta R is larger, that is the separation between the two electronic states have larger values of separation between the two nuclei. The larger, so when delta R becomes larger, the difference delta nu is for the maximum Frank-Condon factor can be observed. So when the separation becomes larger, that is when there is a greater separation Re single prime minus Re double prime. So if delta R is larger, then delta nu can be chosen in order to maximize the Frank-Condon factor. For example, you see that in this diagram in part number B, RE double prime is not equal to RE single prime, because RE single prime is larger than RE double prime. And of course, the dependence of the wave functions on the upper electronic state and the lower electronic state will also be different from each other. So you see that I have chosen the central point of the lower vibrational level, but a shifted point from the upper electronic, from the upper potential, in order to optimize or maximize the Frank quantum principle for this particular transition. Now let's discuss the continuous spectrum. If absorption transitions lead to energies in the upper electronic state above its dissociation energy. Now you see that I am talking about states above the dissociation energy. If absorption transitions lead to energies in the upper electronic state above its dissociation energy, unbound states are reached with non-quantized energies, because these energies or these levels are the unbound state levels lying above the dissociation energy, for which these states have energies which are unquantized or non-quantized. The intensity distribution I as a function of nu is then continuous, because if the upper state above the dissociation energy is not quantized, then of course the transition from such states will follow the transitions which are unquantized. A similar situation arises if the energy of the upper state is above the ionization state of the molecule. So you see that here in this paragraph, I am actually discussing two different states. One is the state of the molecule. In the first case, in the first instance, I am considering the states above the dissociation energy, of the molecules, where the energy levels are continuous, and the transitions from such levels will not be quantized. And the second one is I am discussing the levels above the ionization energy of the molecule. So you see that if there are some levels which are above the ionization energy of the molecule, then of course above the ionization of the molecules we have the continuous band of energy. So under that condition, that is if we are considering the transitions from the levels above the dissociation energy of the molecule or the levels above the ionization energy of the molecules, then of course those levels are not quantized level, and therefore the energy, therefore the flow of energy or the transition from such levels will also not be discrete. So before I this paragraph, let me go through this diagram first, so that when I go through those paragraphs, you can really understand what is happening. So first of all, excitation 1. You know that here in this diagram, I have shown two excitation number 1 and excitation number 2. Excitation number 1 of a bound Rydberg level in the neutral molecule. You know that here transition 1 belongs to red curve, and the red curve is the curve belonging to the neutral molecule. This is the molecule is not ionized. The molecule is neutral, though the molecule is excited. And you know that for this red curve, I have used the symbol M star. M star means that the molecule is in the excited state. The molecule is still neutral, but in the excited state, because the ground state is this one, shown in blue. So the transition has been considered from the vibrational level in the ground electronic state to one of the vibrational level in the neutral molecule, but the molecule is excited as M star, and I am considering the transition 1, that is from the lower vibrational level to E star. So actually E star is actually the vibration level that we are accessing through transition 1. Now consider end of the transition. from the ground vibrational level or the from ground molecular state of the molecule to the vibrational state EI. EI is actually the ionized vibrational state because here the black curve corresponds to M plus. M plus means that the molecule is ionized. So the black curve corresponds to the curve of the potential for the molecule which is ionized. And the lowest level of this ionized molecule has energy, vibrational energy EI. And this EI is actually the ionization energy. So you can access the ionized molecule, that is, you can ionize the molecule through the transition number 2 from the ground state. So from the ground state, if you consider transition number 2 to the level EI of the ionized molecule potential M plus, then of course here the molecule is ionized. So when the molecule is ionized, it means that all the levels above EI have an energy which is continuous. That is, the levels are not quantized. So all the levels above EI up to E star, because I am not considering the levels above E star, so I am considering the levels EI and E star. So E star is actually the excited molecule, is actually the vibrational level of the excited molecule, and the molecule is not ionized. Whereas EI is actually the lowest energy or lowest vibrational level corresponding to the excited molecule, which is M plus. So the levels above the ionization energy EI up to E star, all the levels are continuous in this region. So this is the continuous band of energies. Now you see that let me describe the mathematical equation for transition 1. This is M, that is the molecular energy in the ground state, that is M Eg. Eg is actually energy of the molecule in the ground state. So this is the molecular energy in the ground state plus h nu. That is, you are shining a laser with a frequency h nu for the excitation, as for the excitation number 1. So you have a photon incident on the molecule. The photon energy is h nu. Then of course the molecule gets excited, and the molecule will have energy m of E star, because you have raised the molecule to the energy level E star, where the molecule is still not ionized, the molecule is still neutral, and its excited level E star is lying above in energy than the ionization energy of the molecule. And you know that this level E star that you have accessed is actually belongs to the discrete spectrum, because the ground state energy is fixed. The photon energy is also discretized. So the addition of these two energy will raise the molecule to a state E star, which is also discrete in energy, that is fixed in energy. Now consider the transition number 2. The molecule M of Eg, that is the molecule is in the ground electronic, is the ground state energy of the molecule is Eg, and you are incident, and photon of energy E nu is incident on the molecule. Then the molecule is ionized, represented by M plus, singly ionized molecule to an energy state EI, where EI is the ionization energy of the molecule, plus you know that some energy is left, that is the h nu is actually the energy that corresponds to the ground state of the molecule to the level E star. But you know that the same photon is incident for the transition number 2, and it ionizes the molecule. Then the rest of the energy from the level EI to the level E star, this much difference of energy will appear as the kinetic energy of the electron, of the Rydberg electron, which has been ionized. So this electron is actually occupying, any energy of electron will be occupied, any difference of electron energy will be occupied. Moreover, the excitation of the molecule above the ionization energy could be in any state. So it is could be in EI state, or it could be in a state between EI and E star. So the molecule it is itself could be in any state between EI and E star, but has been ionized, and the electron which will come out from this molecule will gain some kinetic energy due to the difference in energy between the EI state and the E star state. Now you see that when we consider the emission spectrum, then this E star level will will decay through auto ionization to the level EI. So an auto ionization will takes place from the E star level to the EI level, and then from the EI level we shall have the transitions downward. So you see that this is just I explained this one, and you know that here I have labeled these two curves as red curve, for example A star plus B, where A star is one of the nuclei in the molecule that has been excited, whereas the second molecule is in the rest position, is in the ground state. And you know that this happens when we consider the Rydberg atoms. That is, in the Rydberg atoms, if there are two electrons in a molecule, one of the electron will remain one of the molecule, one of the nuclei. For example, here nucleus B will remain in the ground state, whereas the second nuclei will be excited. For example, A star is the excited nuclei. Whereas the black curve corresponds to A plus B, where A plus stands for that the nuclei A has been ionized, whereas the nucleus B is still in the ground state. And you know that this happens in the Rydberg atoms, that in the Rydberg molecules, that is in the Rydberg molecules, one of the molecules is keep on exciting to the higher and higher and higher levels, whereas the second nuclei will remain in the ground state. For example, according to this picture, the nucleus B will remain in the ground state, whereas the nucleus A will be raised to higher energy states, and ultimately it will be ionized. Now you see that having explained the figure, I am going through very quickly through these paragraphs. In the molecular spectra, the ionization continuum is superimposed by many discrete lines that correspond to transitions into higher vibrational or rotational levels of the bound Rydberg states in the neutral molecule. You know that while discussing the neutral molecule, the curve is a red curve. Red curve is the curve that corresponds to the neutral molecule. So when you raise the Rydberg molecule into the nuclear, into the neutral molecule, the states can further be raised due to the vibrational or rotational levels, which can further be accessed from the bound Rydberg states. Although the electronic energy of these Rydberg states is still below the ionization limit, the additional vibrational or rotational energy bring the total energy above the ionization energy of the non-vibrating and non-rotating molecule. For example, in the curve red, the red curve belongs to the neutral atom, and of course the Rydberg, it represents a Rydberg state. And the Rydberg atom, due to its vibrational and rotational level, is in the state E star. And you know that E star is lying above the ionization energy of the molecule itself. But you know that we have accessed this E star level as the neutral, as the level in the neutral molecule. Although the electronic energy of these Rydberg states is still below the ionization limit, that is the electronic energy, that is the electronic energy belonging to the red curve is lying below the ionization limit. The additional vibrational or rotational energy bring the total energy above the ionization energy. For example, the energy of the E star is lying above the ionization energy of the molecule due to the molecule. Such states can decay by autoionization into a lower state of the molecular ion, where part of the kinetic energy of the vibrating and rotating molecule core is transferred to the Rydberg electron. Because the molecule is ionized, that is the Rydberg molecule is ionized, and the Rydberg electron which has left the molecule will to that molecule the kinetic energy due to the difference of energy between E star and EI, that energy will be transferred to the Rydberg electron, which gains sufficient energy to leave the molecule. And this is through the autoionization process. That is, the states of the molecule E star will decay to the EI states through autoionization process. And the difference of this energy will appear as the kinetic energy of that Rydberg electron. Because this is the electron which was belonging to the Rydberg atom in the molecule, which is the atom number A in these levels. So the electron has left the Rydberg atom, and then it will gain a kinetic energy due to the difference of energy between E star and EI. So this is what I have explained over here. So let me go through this paragraph once again. Such states can decay by autoionization. That is, the states E star can decay by autoionization into a lower state of a molecular ion, say EI, or any level between EI and E star, where the part of the kinetic energy of the vibrating and rotating molecule core is transferred to the Rydberg electron, which gains sufficient energy to leave the molecule. The situation is similar to that of a doubly excited Rydberg atoms, where the energy can be transferred from one excited electron to the Rydberg electron or the Rydberg atom. This process is generally very slow, 10 to the power minus 6 to 10 to the power minus 10 second, because the coupling between the motion of the nuclei and the electron is very weak. And you know that in the Born-Oppenheimer approximation, we have also considered that the coupling between the nuclear motion and the electronic motion is very weak. And the same thing is applicable over here. In fact, within the adiabatic approximation, it would be zero. That is the coupling between the nuclear motion and between the electronic motion will be equal to zero under adiabatic approximation. And so the process is generally very slow, lying in the range of 10 to the power minus 6 to 10 to the power minus 10 second. And you know that normally this Rydberg state, that is the state where the Rydberg electron is ionized, is actually accessed through doubly excited Rydberg atoms. That is, a single excitation is not done, but the Rydberg atoms are excited in two different steps, known as double excitation. And the double excitation is what I am going to discuss now. For example, this G state is the state of the molecule in its ground state. Now the molecule will be raised to the state number I. So this is I is the excited state of the molecule. And when the molecule is excited in between these two extreme limits, then this state may be referred as the ith state. And ith state is the state higher than the ground state. So when the molecule is in the ith state, this molecule can further provided, or this Rydberg atom can further provided energy so that the ith state can be raised to the kth state. And you know that in the kth state, the molecule has been shown to be M star, which is mean that the molecule is in the excited state. And here the molecule occupies an energy E star, and the E star is the energy which is beyond the dissociation energy of the molecule, which I have explained in the previous diagram. And when the molecule is in the E star state of the molecule M star, then the autoionization takes place and the molecule will fall to the ionized state of the molecule F. So F will be the state of the ionized molecule. That is, the molecule is now in the ionic state, and the electron, which we here call as the Rydberg electron, has left the molecule. And under the condition that M star in the K state decays into M ionized, that is, the molecule is ionized in the F state, and the difference of these two states will appear as the kinetic energy of the electron. The caption of the figure is two-step excitation of a molecular Rydberg level. That is, the Rydberg level is the kth level or the kth state of the molecule, which transfers by autoionization into the lower F state of the molecular ion. So F state is actually the state of the molecular ion, not the neutral molecule. The difference of energy is given to the free electron. So you see that this is what I have discussed in this second paragraph. Now let's follow the last paragraph. So you see that I have discussed the double excited Rydberg atoms, and relevant to this last paragraph, I have explained the figure in which the double excitation takes place and the molecule is raised to the level which is beyond the dissociation energy of the molecule, and then the molecule through autoionization decays to the lower state, which is the F state, and which is the molecular ionization state of the molecule, and where the difference of energy between the M star state and M plus state will appear, that is the energy separation, that is the energy difference between the K electronic state and the F state will appear as the kinetic energy of the Rydberg electron. The vibrational or rotational autoionization of molecules represent a breakdown of the Born-Oppenheimer approximation. That is an interaction that is an interaction between the nuclear motion and the electronic motion will come into play. So we can say that the Born-Oppenheimer approximation is broken down through the autoionization relaxation of the molecule. The decay of these levels by autoionization is very slow and the lines appear sharp. In the figure on page number 154, an example of the excitation scheme of autoionization Rydberg levels is shown. And this is what I have discussed before. The Rydberg levels are generally excited in a two-step process from the ground state G to the level I by absorption of a photon from a laser, and the further excitation from the state I to the state K by a photon from another laser. The autoionization of the Rydberg K state is monitored by the observation of the resultant molecular ion. So you see that when the molecule, that is when the Rydberg level K is relaxed through the autoionization, the molecular ion is formed. So the detection of the molecular ion will confirm that the Rydberg level K state has decayed by autoionization to one of the lower state, which is the F state I have explained earlier. A section of autoionization spectrum of the lithium diatomic molecule with sharp lines and a weak continuous background caused by direct photoionization is shown in figure number 150 on page number 157. For example, this figure. These sharp lines, sharp peaks actually due to belongs to the autoionization process in the molecules, where the Rydberg states relax through the autoionization process to the lower states, and the molecule, excited molecule, becomes ionized. And of course, at the same time, the Rydberg electron is created. And you know that these are the gamma values equal to 0.02 centimeter inverse. That will give you the amplitude of these curves. So you see that these are the three curves, and these three curves are actually the autoionization spectrum of the lithium molecule. And these curves are also called the Fano profiles. It is called a Fano profile because these curves are not symmetric. On one side, on the left hand side, these curves are expanded, and on the right hand side, these curves decay very quickly. And gamma is actually the width of these curves at half maximum in wave number units, which is gamma is equal to 0.02 centimeter inverse, and in the unit of seconds is equal to 1.3 nanosecond. Similarly, for the second curve, that is this is the second autoionization spectrum of the lithium molecule, giving you the second curve is having different widths in terms of wave number and units of time. And similarly, the third curve. And you see that there is a background over here, and in the background you can also observe some spectrum. These background spectrum actually belongs to the direct photoionization of the molecule. That is the photoionization of the molecule through the process 2 that I have mentioned earlier. The caption of the figure is section of autoionization spectrum of the lithium molecule with the three lines showing a Fano profile with the different widths. So you see that if you have the lithium diatomic molecules excited in the same way that I have explained before using Rydberg nuclei, using Rydberg atomic states, then of course you will notice that three curves for the case of lithium molecule can be observed as Fano profiles, and these curves belongs to the autoionization process, in which the molecules in the excited states are converted into the molecules in the ionized states, and an electron is also emitted in the process. So with the lithium molecule, we can observe these three spectral states belonging to these peaks belong to the autoionization process, whereas the rest of the background indicates the spectrum associated with the direct photoionization process of the molecule. A section of the autoionization spectrum of the lithium molecule with sharp lines and a weak continuous background caused by direct ionization is shown. The lines have asymmetric line profile, also called Fano profile. The reason for this asymmetry is an interference effect between two possible excitation paths to the energy E star in the ionization continuum. So you see that this is due to two processes that we are carrying out. One is the direct, one is the excitation of the molecule to the state E star, whereas the direct excitation of the ionization states of the molecule. So due to these two processes, there could be an interference effect, and due to that interference effect, an asymmetry can be observed in the Fano profiles of these curves. Now you see that here the interference is being explained. And you know that this in the B, I have the resultant. This is the Fano profile. I have shown the Fano profile, which has a limited magnitude. in the form of a peak, and you can notice the spread of this Fano profile. You know that this spread is asymmetric about this dotted black line. There is a sharp decay on the right hand side, and you know that there is a very slow decay on the left hand side. So let me read the caption first in detail. The figure number A represents two excitation from the state I. I am here not talking about the ground state, but talking about the state I. That is, the molecule is already is in a state I, is in a Rydberg state, and here I am raising the molecule through transition number 1 in the K state, and also through transition number 2 to the E star state. And you know that the K state can decay to the E star state through autoionization. And D1 and D2 and D12, I shall be explaining them in a minute, exactly a minute ago. I shall be going to explain them. That is, what is D1, what is D2, and what is D12. So let's concentrate on this figure. So you see that this sigma D. Now about figure B, resultant Fano profile with asymmetric line shape. You can see that the line shape is asymmetric. Sigma D is the absorption cross section for direct photoionization, and you know that this may correspond, this sigma D is the absorption cross section for direct photoionization. And you know that the photoionization process takes place between the kth state and the this band which represents the ionization energy of the molecule, and beyond that one the spectrum is continuous. That is, the states between EI and E star are forming a continuous band of states. Now I am going to explain this figure with the help of these paragraphs. The excitation of the Rydberg level, that is the K state of the neutral molecule from the level ith with the probability amplitude D1 with the subsequent autoionization. So you see that the level K state of the neutral atom will be raised from the ith state using the probability amplitude D1. So D1 represents the probability amplitude for the transition from the ith state to the kth state, where you know that the k state belongs to the state where the molecule is in the neutral position, and this state is lying above the dissociation energy of the molecule as well. The direct photoionization from level ith with probability amplitude D2. So D2 is the probability amplitude for the direct photoionization from the state number I to state with the band indicated over here. So D2 belongs to the probability amplitude. D2 is the for the direct photoionization. When the frequency of the excitation laser is tuned, the phase of the transition matrix elements does not change much for path 2, because path 2 consists of a band of frequencies. You may consider that one a continuous band of frequencies. So a very high precision of tuning from the laser is not required, but much more for path 1. That is when we want to access the path 1, where the upper level is a discrete level because of the frequency tuning is tuned over the narrow resonance of a discrete transition. So you see that in order to access the kth state, the laser tuning is required, and a very precise tuning wavelength is required to access such a level. The total transition probability of the system together, which is represented by PIF, is equal to absolute square of D1 and D2. This PIF, however, therefore changes with the frequency, because T1 will change, will depend upon frequency. So therefore changes with the frequency of the excitation laser, because the interference is on one side of the resonance destructive and on the other side constructive, resulting in asymmetric line profile. So you see that since there are double transitions simultaneously, so on one side it could be destructive, on the other side it could be constructive, and due to this one, there could be a Fano profile. That is, the profile will not be symmetric. Continuous spectra can also appear in emission if a bound upper level is excited that emits fluorescence into a repulsive lower state. So you see that if you want to get a continuous spectrum from a molecular system, then you see that the upper level should be a bound state, whereas the lower state or the potential of the lower state should be a repulsive lower state. That is, the lower state should be an unstable state. So the transition from the upper stable state to a lower unstable state or a lower repulsive state will give you a continuous spectrum. Such a situation is seen in the excimer lasers, where which have stable excited upper states but an unstable ground states. And this is also shown in equation in the figure on equation on page number 161. So let me explain this figure. This figure actually a level scheme of the sodium potassium molecule with excitation and discrete and continuous spectrum. This black lower electronic state of the molecule has a label X1 sigma is the lower electronic state of the molecule or the ground electronic state of the molecule, and this level, which is I have indicated only a single level, is actually the lowest vibrational level lying in this electronic state. So I can raise, using a laser excitation, I can raise the molecule from this lower vibrational states of the lower electronic state to the upper electronic state. For example, this level. Which belongs to the red curve. So I can raise the molecule from the lower vibrational states of the lower electronic state to this vibrational level indicated by the black horizontal line of the electronic state represented in red. This electronic state represented in red has molecular state represented by D1 pi, whereas the black electronic state represented by 3 pi. And you know that these two are the bound molecular states. And this is the one vibrational level which also belongs to the molecular state. And I have also shown one repulsive potential state, that is an unstable electronic state of the molecule represented by 3 sigma plus, is also shown in red just above the ground electronic state. So you see that there could be more electronic states between the ground electronic state and the red repulsive state, which I have not shown. So I have shown only the red repulsive state of the molecule. Molecule cannot exist in this state. There is a small region in the red curve that has some depth over here, which means that this region of the red curve is actually the region where you can have a stable molecule, where the molecule could be stable. So if you consider the transitions from the upper state, in this region of the red curve, then you see that you can obtain discrete lines, because this is the bound potential. Here the potential is bound. So the molecule can exist in this state. And in the other part of this region, or in the other part of the red region, the potential is a repulsive potential. That is, molecule cannot exist in this potential. And the transition from the upper state to any part of this repulsive potential is possible, giving you a continuous fluorescence spectrum represented by a typical line shown in green arrow. So you see that many green arrows could be possible, giving you a continuous fluorescence spectrum. Whereas the blue arrows from the same upper state to these bound states in the red region will give you discrete lines. So this red arrow, a part of red curve potential, has some repulsive part and some attractive part where the molecule could be stable. Now you see that I go through this picture very quickly because I have explained all the things about that figure. So let me go through very quickly. For illustration, the emission spectrum of an excited state of the sodium potassium alkali molecule is shown in figure number 161. The state is a mixture of singlet and triplet states due to strong spin orbit coupling. Therefore, the transition from this mixed state into the lower singlet as well as the triplet state becomes allowed. So this molecule, which is the sodium potassium molecule, can have two states, the singlet states and the triplet states. So if you excite the molecule, even then there are two states. 1 pi is the singlet state, 3 pi is the triplet state. So the molecule can exist in these two states with the two different with these two different potentials. And in the lower, the molecule in the ground state can also exist in two states. For example, this is the ground state. It is represented by x1 sigma. It is the singlet state. And there is another state which is a 3 sigma plus state, which is the singlet state, which is the triplet state. So you see that each state of the molecule will have two states. One is the singlet, the other one is the triplet. So the transition from the triplet to triplet and from the singlet to singlet are possible. So here for this particular molecule, the transition from the singlet, that is the d1 pi, to the singlet x1 sigma state will give you the discrete lines. Whereas the transition from the triplet state 3 pi to 3 sigma plus state will give you triplet states. Transition between triplet states. So the singlet to singlet and the triplet to triplet transitions are allowed for this molecule. The emission into the stable singlet ground state x1 sigma shows the discrete lines. The emission into the weakly bound lowest triplet state, which is the 3 sigma, shows on the short wavelength side a section of discrete lines terminating at bound vibrational rotational states in the shallow potential well of a 3 sigma state, and on the long wavelength side a modulated continuum spectrum terminating on the energies above the dissociation energy of a 3 sigma state. That is, you see that in the red curve there could be some states, discrete states, following the sigma 1s transitions from d1 pi states, and there are also some states above the dissociation energy of this molecule where the potential is a repulsive potential and giving you a continuous spectrum. And the transition from the 3 pi to this 3 sigma plus state will occur for the continuous fluorescence. The intensity modulation reflects the intensity modulation reflects the Frank-Condon factor that is the square of the overlap integral between the vibrational wave functions of the bound level in the upper electronic state and the function of the wave function of the unstable level in the repulsive potential above the dissociation energy of the lower state, which can be described by an Airy function. So you see that in this paragraph I am talking about the Frank-Condon factor between the transition from the bound triplet states of the upper electronic of the upper molecular state to the repulsive state of the molecule in this region. This repulsive state shown in the red part and which is above the dissociation energy of the molecule. This is responsible for the continuous fluorescence. And in this region, where the potential is repulsive, an Airy pattern and Airy type pattern as the probability distribution of the Frank-Condon factor can be observed. The frequency nu, which is actually the difference between two potentials, excited energy in the energy of the excited potential and the energy of the lower ground potential, and the wavelength lambda is equal to c over nu of the emission depends on the internuclear separation r, because the emission terminates on the Mulliken potential of the repulsive potential state, dashed blue curve in figure number on page number 162. So let me show you the Mulliken potential of the repulsive lower state represented by dashed blue curve in the figure on page number 160 number 2. This is the figure on page 162. And you can see here a blue curve. This blue curve actually representing a potential U of R, that is the Mulliken potential is represented by the blue curve. The caption of the figure is vibrational overlap and the Frank-Condon factor for continuous emission. And you know that here I am considering the same red curve over here. You may consider it the same red curve or the repulsive potential in this region belonging to the potential 2 of the ground level. And the potential in which the molecule is excited is given by E single prime. That is the E potential single prime as a function of R. This is the potential of the excited molecule, and below is the repulsive potential of the molecule. And the three transitions in the three dotted lines projected from the upper electronic state to this repulsive potential have been shown. So you see that the transitions will occur within the values of R permitted by the Mulliken potential. Beyond the Mulliken potential, there will be no transitions. And the transition probability of these transitions as Airy pattern have been shown for three different vibrational levels of the repulsive potential. So this is the vibrational level V22, this is again V22, this is again V22. So these V22 have different values. For example, maybe 4, maybe 8, maybe 12, and something like that. But there is no need to specify the specify these quantum numbers, vibrational quantum numbers. So I have given these. I have specified these three different vibrational quantum numbers on the repulsive potential curve. And I have also shown the transition probability following the Frank-Condon principle, and these transition probabilities are represented by the Airy patterns, which I have also plotted across these vibrational curves. And you know that this blue line, dotted blue line, is actually the Muller potential. So the transitions from the upper electronic state to the lower repulsive state can occur only within the region of R permitted by the Muller potential. And you know that here on the left hand side, I have shown the intensity which follows the absolute square of the probability of the Frank-Condon principle. So the probabilities of the probability of the amplitude of probability I of nu, that is the intensity as a function of a frequencies or the wave numbers, have been shown over here on the left hand side. So this upper curve, this curve on the left hand side is continued to the second curve in between the two main curves. One is this curve, and then there is another curve on between them. So the first curve on the left is continued to the middle curve as far as the intensity of the curve, which is proportional to the absolute square of the Frank-Condon principle, or the square of the because this absolute square of the product of the integral of the product of two vibrational functions is actually the Frank-Condon factor. So you see that for the sodium potential, for the sodium potassium molecule, NAK molecule, the measured emission spectrum is shown over here. The spectrum starts from 625 nanometer, and you should follow the progress of this spectrum towards the left, towards 630 nanometer. You see that from 625 to about 610 or to about 630, you will notice that the spectrum is discrete, giving you a single line. These are the Fano spectrum, or the Fano profile of the spectrum. All these lines are discrete. And you know that at further you will observe a continuous region of the spectrum. This is the continuous region of the spectrum. And this spectrum is further going to extend. And since I cannot extend the figure on the left hand side, I have extended the figure at the bottom side. So you can see that this is almost a continuous spectrum. So look at this continuous spectrum. This is the continuous emission spectrum. Following, you know that these are the Airy patterns, almost very much like the Airy patterns in the continuous region of the spectrum, following up to 695 nanometers or up to 700 nanometers. And this is the spectrum of the sodium NAK molecule, and this is the emission spectrum. And you know that this spectrum emits discrete spectrum as well as the continuous spectrum, which I have explained over here. And you know that this is the end of slide number 18L. This was the 12th lecture of the molecular physics course on diatomic molecules. But you know that there is also very important type of molecules reference, which is the polyatomic molecule. You know that I am finishing this course on diatomic molecules, because the polyatomic molecules will take me another at least 20 or 25 lectures to explain that one. And you know that such a very lengthy course covering whole atomic physics part and also many lectures on diatomic part, at least 12 lectures on diatomic part of the molecular physics are quite extensive. And if I follow the polyatomic molecules also, then the number of lectures, there will be another 20 lectures on polyatomic molecules. And the course will be so extensive that it cannot be taught in any course, either on the MPhil level or the MS level or the PhD level, unless the course is split separately into the atomic physics part or into the molecular part. I hope those students who are carrying out research in the field of molecular physics, I have presented the diatomic molecule, and following this one, they would be able to quite understand the diatomic molecule, and on similar pattern, they will be able to understand the polyatomic molecules following any textbook. So this is the end of my course on atomic and molecular physics. So I shall be soon will be starting by the grace of Allah another course in continuation. So you see that so far I have covered three courses. I have covered a course on Fourier optics. I have covered a course on laser physics, and the third course, this is the current course which I am going to end, is the course on atomic and molecular physics. So this is the end of this course.